Okay, everyone, can you hear me? We're going to go ahead and get started. So I'm David Lindell. I'm assistant professor in the Department of Computer Science, and it's my pleasure to introduce Michal Irani. Michal Irani is the dean of the Faculty of Mathematics and Computer Science at the Weizmann Institute. She's also one of the eminent members of the computer vision community. She's works generally in the area of computer vision, artificial intelligence. She has work in pioneering work in video information analysis, the internal structure of images. She's won numerous awards. I'll just say a couple of them. She's won Best Paper at ECCV twice, runner-up to the Mar Prize at ICCV twice. She's also a member of the Israel Academy of Sciences and Humanities, and it's really a pleasure to have her here. So with that, please join me in giving a warm welcome to Michal Irani.
Hi. Thanks for inviting me. Actually, the main thing I'm working on, I spoke about it yesterday. I assume most of you were not there. It's about reading minds and machines. But this is not what I'm going to talk about today. Today, I'm going to talk about some older work of mine, older being the last 5 or so years. I mean, I started in 2017 and up to recently. But I think still it's very relevant for people working in computer vision and deep learning. And what I'd like to talk about is deep internal learning. What do I mean by that? Well, we're all used to external learning. We train a deep network and lots of data, train it for hours, days, weeks, then freeze the network and apply it to new data as it comes in. And this does amazingly well. But it does well only when you have enough training data. But what happens if you don't have enough training data? Or what happens if your new test data is outside the distribution of your training data? In those cases, deep learning fails miserably. And what I'd like to show you is how we can train a deep network without ever having seen any prior examples by training on a single image, the test image alone, the one that we want to do the inference on. And it turns out that this has lots of applications. I refer to this as deep internal learning. We train on the information inside a single image. And it turns out that this, we can apply it to lots of things. Super resolution, both spatial in images and temporal in video, image dehazing, image segmentation, transparency separation, diverse image and video generation, and much more. Now, I don't claim that this would necessarily be state of the art compared to very extensively trained networks. But the nice thing about this can be trained on a single example without any prior examples, without any prior knowledge of the world. Okay? So let's see how we can do this. How can we train a network on a single image? Well, it turns out that there's a lot of redundancy inside a single natural image, both within the original scale as well as across different scales. When I say within scale, I mean that if you see a small patch once inside the image, you'll almost surely see it many more times inside the same image. Here I'm showing you large patches, but in practice I'm talking about much smaller patches, 5 by 5 pixels or 7 by 7. And this property has been used by us and many others for lots of applications in computer vision well before deep learning, image completion, image denoising, visual summaries, and more. Less commonly used, but also very powerful, is the recurrence of patches across scales in an image. What I mean by that is if you take the image and scale it down, that almost any patch in the original image, you'll almost surely find an almost identical patch to it in coarser scales of the image without scaling down the patch, which means that in the original image, you had small patterns repeating in multiple sizes. And again, I'm showing this for large patches, but I'm talking about much smaller patches. And again, this has been used by us and by others for lots of applications, including fractal image compression, super resolution from a single image, blind deblurring, blind dehazing, and more. Now you can say, well, this is a very contrived looking image. Does it go beyond images with such strong repetitive structure? And the answer is yes. If you go to small enough patches, it's true for almost any patch and almost any natural image. For example, if we look at an image like this, then here is a patch along the edge. It will repeat many more times along the same edge. Or if you look across scales, then edge patches will repeat as is across different scales. And similarly, corner patches without scaling down the patch. Now you can say, okay, repetitive structure, edges, corners. What happens if I go to an image like this? Is this still true? Well, let's zoom into this image. And you see that locally you have the same patterns, okay? This fractal-like property is a very, very strong property of natural images. And we showed it in our ICCV 2009 paper. We showed it empirically. We took millions of patches from hundreds of images, natural images, indoor, outdoor, man-made, natural. And it turns out that this is true for almost any patch in almost any natural image. So this was really nice, and we used it for lots of applications. The nice thing about this repetitive structure is it's totally unsupervised. It doesn't require any additional information beyond the input image. Okay, all the statistical information is found inside the single natural image, and it forms a very strong prior for solving ill-posed inverse problems in vision. The bad news in the past few years, this has been has been completely outperformed by deep learning methods, which is, of course, very depressing. So, as I said, deep learning does better than any of these internally trained networks. As I said, I was really depressed about this for a while. So for a long time, I was really depressed about this. But then I said, on one hand, we have this deep learning, which is amazingly powerful, but requires tons of data. It's really data hungry. We have no idea what it's learning. And on the other hand, we have this internal redundancy, which is a really simple property. We understand that physically, requires no prior knowledge, self-supervised, but doesn't do as well as deep learning. Is there a way to combine the power of those two complementary methods? And I was thinking about this for a long time. And then luckily, my former PhD student, who was then a master's student, Asaf Shuchel, came up with this brilliant idea of doing deep internal learning. That is to say, train as an image-specific CNN at test time on the data extracted from the test image only. Okay, so the first thing we try to do is apply it to super resolution. Now, in super resolution, in super resolution, you have a low resolution image. The resolution is determined by the density of the pixels, and you want to increase the resolution. So, in super resolution, the density is determined by the resolution is determined by the density of the pixels, and when you do super resolution, you want to increase the resolution of the image. You want to increase the density of the pixels, but you don't want to just stretch the image. You don't want to just interpolate it. You want to be able to recover new information that is smaller than a pixel size in the original image. That's the difference between interpolation and super resolution. And by far, the current leading methods are deep learning methods, or what I call external deep learning methods. And their idea was, let's train a network on lots and lots of pairs of low resolution, high resolution images, right? You'll train a network to receive a low resolution image and to output a high resolution image. And you can train it on as many images as you want because it's very easy. Just take a good high quality image, downscale it, and you have such a pair, right? So they trained this network for days, and then fix it, apply it to a new image as it comes along, and boof, here is the outcome, super resolved image. And amazingly, when they did this, this gave immediately about 2 dB improvement in PSNR compared to anything that existed prior to deep learning. But when Asaf and I checked this, we found out that these networks work only under ideal conditions. And what I mean by ideal conditions is, remember, we generated those low resolution by downscaling the high resolution images. This was usually done with ideal bicubic downscaling, okay? But you know what? The world is not ideal. When I take an image, I slightly move my camera. This is not an ideal low-pass filter. And the next time I'll take an image, I'll move my camera differently. So the correct downscaling or the correct blur with which the low resolution image is generated is not camera specific. It's not even photographer specific. It's image specific. And it turns out that when you gave those networks real low resolution images or images that were not downscaled ideally, they didn't do any better than interpolation. And I'll show you this shortly. So we said, well, let's remove this external thing and let's adapt our networks to the internal statistics of the specific image and its own internal degradation. And the idea was the following. We called zero shot super resolution, ZSSR. It's no nation. It's just, okay. And this was a CVPR 218 paper. And the idea was the following. Here's your low resolution image. That's the only image you've ever seen. You have never seen another image in your life. What we're going to do is the counterintuitive thing and downscale this image even further to generate an even lower resolution image. And in a moment, I'll say how we downscale it. Okay. And then we train a very light image-specific CNN to increase the resolution of this image back again. And the loss is it has to recover back the original image. Okay. And once trained on this image, we can then apply this network to the original low resolution image to generate the high resolution image. And the rationale here is because you have this recurrence of patches across scale of any image, including this low resolution image, whatever network will learn to increase the resolution of small patches in this small image will also know how to increase the resolution of patches in this original image. Now, of course, training a network on a single pair of input-output is stretching it. So we applied augmentation to the input image. We rotated it, we scaled it, we flipped it. We generated hundreds of such pairs of low resolution, high resolution images, all from the same patch distribution. And this gave us an image-specific CNN. And because the CNN, all it has to do is to learn how to increase the resolution of this particular image, no other image. It's a very light CNN, and we could train it within 9 seconds on V800 GPU, both train and test time. Okay. Now, what about the downscaling? Remember, I said that each image has its own correct downscaling. It turns out that the correct downscaling, the correct degradation with which this image was generated is also the one that if you downscale the image with it, will maximize the similarity of patches across scales. We have an analytic proof of that in our 2013 paper. And later on in 2019 paper, we show how you can extract this correct downblurring kernel by doing deep internal learning on the input low resolution image. And I'll show you this shortly. Okay. But this in principle gives you super resolution in the wild. You can apply it to any data type, any downscaling kernel, and any downscaling aspect ratio. Okay. So let's first look at some results. Here's a low resolution image generated with an unknown downscaling kernel. Here is what happens if you just bicubically interpolate it, blurry. Here is what happened when you applied state-of-the-art super resolution, externally trained super resolution at that time on this image. And if I'll flicker between the two, you'll barely see the difference. The problem is not in your eyes. There is hardly any difference, okay? And the reason is EDSR Plus did amazingly well when super resolving bicubically downscaled images. But once you took it out of its comfort zone, it didn't do any better than interpolation. In contrast, here is what you get if you apply ZSSR, the internal zero-shot super resolution. And if I'll flicker between the two, you'll be able to see the dramatic difference. We are able to add lots of details. And all of this is because we adapt the CNN to the image-specific degradation and the recurrence of patches within this specific image. Here's another example, an old photo downloaded from the internet, post-World War II, Checkpoint Charlie, before the wall was built. We have no idea how this image was generated. Here is bicubic interpolation of this image. Here is the external super resolution. Again, if I'll flicker between the two, there's very little difference. And here is the result of internal super resolution. And if I'll flicker between the two, you'll see the dramatic difference. We can recover the information you see between the two legs of this man over here, the back of the motorbike. We can go well beyond, we can recover information that is smaller than a pixel size and go beyond the Nyquist limit of the original camera. And here is an example. Oh, what's happening with his colors? It's a problem of the projector or of the cable. Anyways, I don't have those purple colors in my, okay, but sorry for, so here is a JPEG compressed image, low resolution. It looks fine on my screen when it's, and if you applied the extra, this is terrible. This is super resolution. Anyways, if you apply the external super resolution, as you can see, it does really lousy. And here is the internal. I'll skip this. It's anyways. You can't see here, but the JPEG artifacts are increased in the externally trained one and disappear in the internally trained one. We didn't say anything about the noise, but the noise repeats. The signal recurs across scales, whereas the noise does not. So the network learns how to generalize for the signal, but it doesn't know what to do with the noise. And of course, we had empirical evaluations. An ideally downscaled image externally did much better. Okay, but we did reasonably well. But once you took it out of their comfort zone to non-ideal images, either downscaled non-ideally or with noise, we did 1 or 2 dB better than the externally trained networks. Now, what about the downscaling kernel? I said that we can extract that from the input image again, right? Remember, here's all we have is the low resolution input image. We don't know what the high resolution image is, but we also don't know what the correct downscaling kernel that relates the high resolution image to the low resolution one. As I said in our 2013 paper, Tomer Michaeli and I proved that the correct downscaling kernel with which this image was generated is also the one that if you downscale this image with it, will maximize the similarity of patches across scales. And we had an analytic proof in that paper, and then we also solved it using iterative optimization, non-convex optimization. We each time we iteratively downscaled, we looked for nearest neighbors, we improved it, solved for the kernel, and iterated like this. More recently, we found a way of doing this with deep internal learning and recover this kernel. We call it kernel GAN. We train a GAN on a single low resolution image in order to reconstruct its kernel. So how do we do that? Well, here's our low resolution input. Again, this is the only thing we've ever seen. What we're going to do is we're going to train a generator to learn to downscale this image correctly. What is good downscaling? We said good downscaling is the one that maximizes a similarity of patches across scales. Okay. How are we going to guarantee that this is what the generator does? Well, we're going to train a discriminator that will sometimes get crops from the input image and sometimes from the downscaled image, and we'll have to tell which is true and which is generated. Okay. And it will generate a map, and the discriminator will try to get better and better. The generator will try to get better and better and fool the discriminator. And when this internal GAN converges, it will converge to the correct downscaling kernel. Okay. Now, note that this generator cannot be just any deep learning network, right? Any deep learning network might generate a garble of patches, okay, may do some mode collapse, and it will generate lots of patches from this image, but it will not look anything like a downscaled image. The discriminator will say, hey, yes, this came from the original input. The generator will be happy because it fooled the discriminator, but this is not what we want. What we want is a downscaled image, okay? And a correct downscaling image is the one that's generated by convolving with the kernel and downscaling. And if you think about it, this is a linear operation, right? It's a linear operation. So the generator has to be a linear network, okay? And in fact, we thought, hey, all it has to be is a single convolution layer with a single kernel, because that's what we're looking for. So that's what we started with. We put the generator, we turned it into a single convolution layer, and we thought that would work, but it didn't work. It was lousy. It gave us lousy results. Here were, for example, ground truth kernels, and here is what it generated. And we kept thinking that we had a bug, and we looked for it and couldn't find it. And then we realized why this was happening. Remember, deep learning methods converge well because there are infinite many solutions, but all of them are good. There is no local minimum, okay? There's no bad local minima, okay? Now, sorry. Yeah. But in our case, there's a single good global minimum, okay? It's the kernel we're looking for. Now, the optimization problem we're solving is not convex, okay? It's not only that thing, it also the generator has to fool the discriminator. It's a very complex loss. So if we just initialize the generator with random weights, it will converge to some bad local minimum. It will not get to this good global minimum, okay? So what we did is we realized that this will never work. Instead, we replaced it with a deep linear network. What is a deep linear network? It's a deep network that has no nonlinear activations, okay? It's no nonlinearities. And if you multiply all these weights from all the layers, you'll get the kernel. So you say, hey, what's the difference? Isn't this exactly the same? No, it's not the same. Why? Because here we had a single good minimum, okay? Whereas here, the network weights, there are infinitely many decomposition of this kernel into weights in this network. All of them will be good, okay? There are infinitely many decomposition of this kernel. There are infinitely many solutions to this deep linear network that will give you the correct kernel, Okay. For example, if this is a good decomposition, that if I multiply one layer with a matrix A and the other one with the inverse of A, it would still give you the same kernel. Okay. And now when we initialize the network randomly, it converges to a good solution. So here is an example of a ground truth kernel. Here is what we had when we had the single convolution layer, and here is the deep linear layer. And you can see that it converges well. And as far as we know, this is the first ever practical use of deep linear networks. Theoreticians have been using deep linear networks to prove things, okay? But as far as I know, this is the first ever practical use of a deep linear network. Okay. So far we saw how we can use deep internal learning to do super resolution with an image-specific CNN. It turns out we can apply it to other types of problems. We can apply it to image segmentation. We can apply it to transparency separation, to image dehazing, and all of this in a totally unsupervised way with no prior examples by training on a single image with an image-specific CNN. So if we look at those three problems, it turns out we can solve them in a single unified way using what we call double dip. And the idea is the following. All of these three problems can be posed in a unified way as a problem of layer decomposition into two layers. For example, the image segmentation can be decomposed into the background layer and the foreground layer, multiplied by a binary mask, okay? Or the transparency separation can be decomposed into the reflection and transmission multiplied by some constant coefficient. And in the case of image dehazing, it's the haze-free image and the air light color multiplied by a mask, which is the transmission map, which is inversely proportional to the depth, okay? And we solve all of these using a single unified way, which is based on deep image prior. Now, I'm sure you're all familiar with deep image prior, but let me just do a quick reminder so that we're all on the same page. Deep image prior by Ulyanov et al., which came at the same time as our zero-shot super resolution, ZSSR, the idea was the following. Let's train, given an input image, you can train a CNN which gets as input noise and has to learn to output this specific image, nothing else. Okay, this is the loss. Now, of course, eventually it will converge onto this image, but when it does so, the weights of this network will provide a deep image prior on that particular image. And they showed that this can be used for solving many inverse problems. For example, they used it for denoising. And interestingly, they showed that when you apply it to a noisy image, then at some intermediate iteration, you'll get a clean version of this image. Of course, if you keep on doing this, it will eventually converge to the noisy image. And we explained this, the reason it does so is because in the clean image, the patch entropy is much lower than in the noisy image. For example, in the clean image, two patches, we saw that there is this recurrence of patches within the image. Two patches will be similar in the clean image, but in the noisy image, they're no longer similar. Okay, so it's much easier for the CNN, which has the same kernel applied everywhere, to output an image whose patch repetition is strong and whose patch entropy is low. So we said, let's use this deep image prior for decomposing images into two layers. And the idea is the following. We use double dip, two different deep image priors. So here's our mixed image, for example, transparency. What we'll do is we'll train two different deep image priors who get different noises. And we'll expect their sum to give us our mixed image, okay? Now, of course, when we train this, eventually this will converge onto the image. But interestingly, when it does so, it tends to decompose the patches into the two different layers because this is a simpler patch distribution in each one of those images as opposed to giving some mixture of patches. And in order to further encourage it to do so, we add an exclusion loss, which penalizes for correlations between patches, corresponding patches across those two images. And this gives us our two recovered layers. Now, of course, this was a simple example where the addition or where they were mixed with a coefficient, but we can also add a masking, a mask that mixes those two layers. And we'll learn that mask as well, also with another deep image prior. And for example, and the difference between the three examples, three different tasks, is just the loss that you put on this mask. For example, if you want to do a segmentation, image segmentation, then the mask, the loss will be a binary. We encourage it to be a binary mask, and we penalize it when it gets farther and farther away from a binary mask. And when you do that, eventually this converges onto the input image. But here is the binary mask that it generated, and here are the two different layers that each one of those deep image prior converged to. It was easier for one deep image prior to output grass patches, and for the other to output zebra patches, and so on. So let's look at results. So for example, in image segmentation, here are input images, and here were the output masks and the segmentation masks. And you can look at some of these. For example, here are those two ladies with the carts. Here are those three soldiers. Or here is a textured image. And again, there's no prior knowledge here. It's just the simplest decomposition into two different distribution of patches. Here is an example of using it for image dehazing. Here is the input image. Here is the layer of the recovered layer of the haze-free image. The transmission map, which was recovered, that's the mask, which is inversely proportional to the depth. And what about transparency separation? So here's a real video. What you see here is you see the statue inside a building. There is a revolving door, okay? And outside, reflected in this door, is the tripod with the camera and a person walking, okay? And so this is a real video of transparency. We applied this to separate them, and you can see the separation into reflection and transmission. It's not perfect, but it's not bad. And we can also apply it to watermark removal. Again, it's a different type of transparency separation and so on. And all of this in a totally unsupervised way without any prior examples by training on a single image, test image alone. So we see there's something very powerful about this recurrence of patches inside an image. And the question we ask ourselves is, can we train again on a single image? And by the way, this predated SynGAN, okay? That many of you, I'm sure, are familiar with. We called it InGAN. And the thought was the following. Let's train, a regular GAN trains on lots of images, learns the distribution of natural images, and then generates new images from the same image distribution. What we said here is let's train a single GAN to learn the patch distribution within a single image, and then generate new images with the same patch distribution, okay? And and then we can do image retargeting, generate lots of images of different scales, aspect ratios, and so on, all from the same patch distribution. So this was our input image. We trained an internal GAN on this image, and here are the output images that we generated. And you can see that it doesn't change the aspect ratios of fruits. It just adds more and more fruits, more and more boxes. It adds more and more rows of watermelons at the top, okay? But locally, everything seems to come from the same patch distribution. Here's another example. You can see that the penguins, they don't get any fatter, just more and more of them are born. Or the columns in the temple and so on, just more and more of them. Now, of course, no one's perfect. The network, it has no semantic understanding of the scene. Again, has no notion of objects or so on. All it learns is the patch distribution in multiple scales. So, of course, if you look at this locally, everything seems to have come from the same patch distribution of the original image. So this is a valid output. Of course, if I were to increase the image, it would be a larger one, and you'd already see two different people. Okay. This is also what happens in the penguins if you stop it in the middle. Okay. And a year ago, we tried to see whether we can train a diffusion model on a single image. Okay. We called it SynFusion. It was an ICML 23. And the idea was, let's take an input video. We can train a single diffusion model on the patches of this input video, okay, to learn to output these. We can also learn the progression in time in this video by generating a new frame conditioned on the previous frame, okay? And so now once we train such as a diffusion model, we can generate new videos all from the same patch distribution with the same types of motions, okay? So these are all synthesized videos generated from this input video. But we can do more than that. We can also extrapolate a video into the future or into the past, okay? So for example, I'll play this in a moment. It's and you'll see when the red boxed frames are real input frames, and once the frame outside becomes green, those are already interpolated frames. Okay, so let me play that. So here's this tornado, and now these are interpolated frames. They never existed in the original video. Okay. And we can also play this video backwards in time to see what happens before it started. Okay. So here is the extrapolation backwards in time. Red is the original, green is synthesized frames. Okay. I'm not saying it's correct or perfect. It's just to show you what this can do. And we can take those balloon videos and also extrapolate them backwards in time, make the balloons go back in time. And I'll play this now. Again, red frames are the original frames. And now all the green ones are already synthesized frames going backward in time. You can see we go hundreds of frames away from the original input frames. We had a few tens of frames, and now we can generate hundreds and hundreds of frames backwards in time. You can see the clouds moving. It learned these motions, and it generates these things all from a single video of a few tens of frames. All right, and now and the last thing I'll show, and with this I will conclude, how we can use this also for doing super resolution in time, zero-shot super resolution in time in real videos. So the idea is the following. You have a video, it has a limited spatial resolution and a limited temporal resolution. And when we do spatial super resolution, we just try to increase the density of the pixels inside the frame. When I talk about temporal super resolution, I'm talking about increasing the frame rate of the video. But I don't want to just interpolate in time, just like I didn't want to interpolate in space. I want to generate new dynamic events that occur faster than frame rate and are invisible in the original video at the original frame rate. Okay, and that's a difference between interpolation and super resolution in time. I want to undo motion aliasing and motion blur, and all of this in a totally unsupervised way with a single input video. So how are we going to do about this? Sorry, just to show you. Just to show you what motion aliasing and motion blur is, and again, I see I have problems with the color of the display. Okay, so what is motion aliasing and motion blur in video? Here you see a fan rotating clockwise all the time, but at some point it will appear to be rotating counterclockwise because the sampling rate, the temporal sampling rate, is not fast enough. And if I freeze this, you'll see the strong effect. So that's motion aliasing. And if I freeze this, you'll see the strong effect of motion blur due to the fact that the exposure time from the moment the camera exposure opened until the shutter closed, the fan moved very fast, and therefore motion aliasing and motion blur. And you cannot undo the motion blur by just interpolating in time. Here is temporal interpolation, okay? It will just play this in slow motion, but it will not undo the motion blur or motion aliasing. Information is already lost in the sampling process, okay? In temporal super resolution, we want to undo both the motion aliasing and the motion blur. So how are we going to go about this? So again, we're going to take our zero-shot super resolution that we did in images, but now we're going to apply it in time. So we're going to use similar augmentations, but here we have two very sophisticated new augmentations in time. One is we're going to generate lower and lower resolution versions of the temporal resolution versions of the video in time. That is to say, as if it's taken with a longer exposure time and sampled more in time, okay? And for example, if this was the original video, this is what the video looks in coarser scale, and here is what it looks in even coarser temporal scales. The frames are the same size. It's just different temporal resolution, okay? So we're going to now train a video-specific CNN to learn how to get a low resolution temporal one and generate a high resolution temporal one. Learn how to undo those effects. And then we're going to use this in order to generate our output high resolution video. Oh, why is this moving on its own? The transition. And by the way, when I synthesize these things, you can see that when I do lower and lower temporal resolution, I synthesize more and more motion blur and more motion aliasing. Okay. So as I said, once you train it on these things, you're going to apply it to the input video to generate your high resolution output. That's one type of interesting augmentation. Another type of interesting augmentation is based on our new observation that patches recur not only across different scales of the video, but also across different dimensions of the video. What I mean by that is, if you take the video, it has X, Y, T dimensions. If you just take the frames are spatial slices of this volume, but if you now take this volume and rotate it so that the one of the spatial axes becomes a temporal axis, and now you take slices of that, you'll get the YT slices. And if you look at them, they look very similar to your original video frames, only you have here aliasing in the temporal dimension, which means you can use the patches in the original video, okay, as examples how to undo the temporal aliasing and increase the resolution in time in those YT slices. So we use all these types of augmentations in our algorithm, and let me show you results. So here's temporal super resolution by a factor of 8. So here's the original input video, okay, at the top left there. That's our result at the bottom left. And here are competitors, and I'm sorry about all these colors. It's not in my videos. NVIDIA Slow-Mo, Flawless, Dane. You can see that they cannot undo the motion aliasing or the motion blur, whereas we don't know what's happening here. Sorry about this. Okay. Where once they cannot undo the motion aliasing and motion blur, whereas we can, because the information recurs across different temporal scales in the video. Okay, so here you can see this result. Here's another example. This rotating disc, at some point, it gets blurry with a lot of motion aliasing. I'm not saying we're not perfect either, but you can see that we undo the motion aliasing, whereas all the others cannot undo the motion aliasing. They're based on externally trained. These are externally trained networks. And of course, it doesn't have to be repetitive structure. Here is one flip. Again, just like in the images, it didn't have to be an image with repetitive structure. Also at time, it doesn't have to be repetitive structure. And you can see our result at the bottom right. Here's another example. In these cases, we have ground truth, high temporal resolution. And you can see the difference between internal learning and external learning. All right, so let me summarize. I think I took too much time. What I tried to show you is we can apply deep learning internally by exploiting the internal redundancy, and this gives us an image-specific deep network. The nice thing is it combines the power of deep learning with internal image-specific or video-specific priors. It's totally unsupervised. It requires nothing but the input image and video. Okay, so it's not supposed to be better than externally trained networks. But the nice thing, there's no notion of being out of distribution. Okay, it adapts itself to the unknown image-specific or video-specific conditions and degradations, and it has many applications. I showed you space, super resolution in space and time, segmentation, dehazing, transparency separation, diverse image and video generation, and there are many other applications. And of course, you can ask, well, can we apply it to other types of domains, other types of signals, audio, medical imagery, EEG? Frankly, I believe that any structured signal has this nice of internal recurrence, only you have to find what are those atoms, what are those elements that recur within these type of structures, but I believe this applies to many types of structures. Can we define a continuum between internal learning and external learning, right? Today we have these two extremes. Either I train a network internally each time from scratch, or we train a network externally on lots and lots of data. And when I'm talking about the continuum, I'm not talking about an externally trained image network and just fine-tuning it on the specific image. No, I'm talking about a continuum. Train on as much information as you have. If you only have one image, train on that. If you have 3 images, train on that. If you have lots of images, train on that. Is there a way to generate a continuum between the two? I think that's what we humans do. And I think deep networks are lacking that at the moment. So thank you for your attention. Sorry for taking so long. Sorry for all the colors on all those slides. And I'll be happy to take questions. What?
Okay, great. Do we have questions?
Yeah, please.
If you could actually approach the mic and maybe line up at the mic, then the folks on Zoom can hear you too.
I can give you my mic. Here.
Okay. So thank you very much for your very engaging presentation. I have two questions. My first question was in one of the first slides when we were just training a CNN on a single image. I didn't understand how do we come up with the ground truth for that, because from the slides I could see that we had like a ground truth full resolution image, and we downgraded that and trained the CNN on augmentations of that. No? Okay, thank you.
The ground truth is the low resolution input itself. We downscale the low resolution image further, and we train to increase the lower low resolution image to go back to the original input low resolution image. Our ground truth is the low resolution image. Once we train that, we apply it to the low resolution image to increase its own resolution.
Thank you. And for my second question, when we were learning the distribution of patches, do we learn the distribution of patches locally? Because I mean, a watermelon has a different patch than like an orange, but those patches were like localized; they were saved. So how?
No, it's a CNN. The CNN uses the same kernels everywhere. It's just each time we take different crops. Okay. When we initialize for the internal GAN, what you saw with the watermelons and so on, we initialize the new image, we downscale it a bit, first bicubically, and then we correct it with the, so we use this as an initial guess. So that's what causes the watermelons to remain where they are and so on. But no, the patch distribution is patch distribution.
Wonderful talk, Michal. I'm intrigued by this last point of somehow combining internal and external learning, and I'm wondering, in the purely internal learning, were there priors that you think could really play a role in overcoming some of the errors? And could you imagine a canonical set of external learning examples that might help boost some of those priors that you could then take advantage of in your internal learning?
Maybe ask the same this type of question.
I don't have a good answer. You know, the priors that we exploited in this internal learning, first of all, the CNN implicitly exploits the internal recurrence within scale, right? Because you apply the same kernels everywhere. So that in a way implicitly exploits the internal repetition within scale. The internal repetition across scales we obtain by downscaling the image and using this as a pair, expecting it to apply. But we didn't add any other types of priors. Now I don't know. I mean, those are the kind of priors that were either implicit due to the architecture of the CNN, or now. By the way, this internal recurrence, if you think about it, self-attention of today's transformer are actually this internal recurrence. Okay, right? They do compute self-attention between different patches. By the way, in my opinion, it's the wrong patch sizes, and they do it without overlaps, mistakes, big mistakes. Okay, but transformers, in a way, the self-attention is exploiting the internal redundancy within a single image. So I don't know. I don't have a more intelligent answer than this.
I think there's a question on Zoom as well. If you could type it into the chat, then we can read out your question for Michal.
Oh,
And
you want me to?
I'll
no.
ask the person who submitted it to type it up, and then we can read it for you.
All right.
Is there, another question?
You want to go up to the mic? It'll be difficult for me to get to you.
Just make sure you turn on the mic once you get there. Should be a switch on the side.
Okay. Yeah. So Thank you for the great talk. I was wondering, like, a lot of these applications that you showed were just possible with using and utilizing the pixel level information and the structure in the pixel level information, but would using some of the like semantic information that the newer foundation models have in their features make all of these a bit easier, or would it like make it lose some of the nice properties that you were showing?
Maybe we need to request that that these features in foundation models also have this kind of redundancy. I don't know if that's what you're asking. By the way, going back to your question, Sven, maybe applying recurrence in transformers. Transformers currently compute self-attention within the same scale, but they don't compute any self-attention across different scales of a single image unit. That's another way of applying these kind of things. I don't know.
Thank you.
Yeah,
Yes.
the question on Zoom, I
Okay.
can summarize that. They were wondering about differences in the learned representations, like what is learned in internal learning versus external learning, and if you investigated that.
I haven't investigated that, but I can tell you that external learning looks for what's common across all images. Internal learning just learns what's common to this particular image. Okay. For example, if you take an Escher-like image, okay, where there things are zoomed in and at some point, I have a hidden slide, I think, somewhere, but I'm not sure. You can see the handrails on or whatever at the fine scale, but you can't see them at the coarse scale. No external image will ever tell you that this is supposed to have those handrails or whatever in the coarse scale. The only image that will tell you that this is supposed to have it is in the same image, elsewhere in the image at a different scale. Okay, these kind of information you will never get from external data. On the other hand, so much notion that is being learned that is common to all the images. This is what's captured in foundation models. So I think in a way, in the internal learning, we're learning the long tail with things that are out of distribution of the general images. I think that's what's captured there.
Thank you. Okay, maybe time for a couple more questions. Yeah, we'll take these two. If you could, yeah.
First of all, thank you for your question, for your presentation. I wanted to know how does it play out in edge cases on devices, and we have zettabytes of data out there on the internet. Training for each one of them overall, how would it play out in general?
You tell me. I'm not claiming that this is the right way to go about training on lots and lots of data. I don't think that's the right way. That's why I was asking if there is a way to develop this continuum between internal and external. Okay. When you have lots of data, you want to exploit it smartly. That's not a smart way to exploit lots and lots and lots of data. That's a smart way to exploit non-existing data. Okay. Yeah.
But like right now, implicit representation of like nerves and image for representation. Like right now, it is very famous, like nerve and other ways to implicitly represent the signal behind the image or 3D scene. So they are getting quite famous. So in that sense, I was asking basically.
But they're also training on the and it takes them, by the way, hours and hours and hours to train. Okay, this doesn't take hours. Yeah, by the way, I don't think nerf is necessarily the right way to go about 3D or whatever. It's a very cool idea, but yeah. But yeah, nerf is now. By the way, if you look at the classical, right, Gaussian splatting, why is it working so much faster than nerf? Because it's using the good old initialization from bundle adjustment as the original input. I think you guys have to know something. There are lots of smart things in computer vision that existed way before deep learning. Okay, people but think that the world started with deep learning. Okay, you're missing out on so many smart ideas, okay, that exist out there, and I think are hurting today's deep learning, the fact that they're not being used, okay? And that's why I'm still teaching in my university also Introduction to Classical Computer Vision, because I think that when people don't know that, they cannot become good scientists. So I think all of you, if you don't know classical computer vision, you should learn it. But yeah, so NERF is good, but it completely ignored classical projective geometry. And once you've added that and Gaussian splatting, poof, all of a sudden you could do things much faster. So that's just a side comment.
Thank you. Just curious if you've done any tricks around it, like with unsupervised learning, because I mean, I'm gonna first ask you, if you were to just do this on any random image and just increase the resolution of it, would that in general improve it, like without you necessarily wanting to check this? Because my end goal is to just use this as a heuristic or trick to kind of improve the resolution of some images, and then you can use that improved image for some unsupervised learning, like examples could be clip or any other thing, just to learn better representations out of like that new data set that you can create from like lower resolution images, right? Basically, you want to augment some data set that you have, and you want to improve the resolution of these images that you have that might be in lower resolution. So the question is kind of, would you say that in general, if you were to let's just apply this thing, would it improve the image?
I'm not sure I fully, I thought that you asked several different things, so I'm not sure I'm answering exactly what you asked. If I think this will apply well to any image, so super resolution, if you apply zero-shot super resolution, it will increase the resolution of any image. How well it will do it depends on the amount of recurrence, of course. The more fractal the image, the better it will be. Okay. By the way, it's important for me to say that zero-shot super resolution, ZSSR, you have to feed it in the correct downscaling. Its default is bicubic, and okay, but you can estimate the degradation. Think about medical images, things like that, things that you have never seen before. They don't have, they won't apply to these kind of things. Internal learning, yeah, it will improve it. How much will it improve it? I don't know, but it will improve it. There's no notion of out of distribution, but you have to compute the correct degradation for each image. Okay. Can you use this for augmentation? Yeah, you could probably use this augmentation. I don't know. But how well it will be, I don't know. By the way, people doing blind super resolution, externally trained blind super resolution, have often used our kernel estimation on lots of images to generate, and then applied external learning with these kind of kernels computed on lots and lots of images. But again, I don't know how to combine the internal and external. I don't have a good answer to that.